Today is 2020 April month, and it is the 14th. It is actually during the Songkran festival that we do not have the break for this year. This is the class number 27 for advanced steel structures, and we are here today to pick up from the last time. Actually, in the last time we came across the idea we saw in Winter bracing paper, and Winters has developed quite several things. He introduced the so-called the ideal stiffness and ideal bracing force. And in reality, the ideal stiffness and ideal bracing force are not actually enough for the reality, because for these two ideal things, these assume that the column of our interest has to be perfectly straight, but again, in reality, the column is not perfectly straight, and the initial out of straightness, initial how is it called, the initial ball, okay, will cause us the secondary moment, and that will bring the column to the buckling earlier than the ideal column. So the development that Winters has made is quite substantial, but still there are more that is required from that point in order to be possible, to make it possible for the designer, because the designer are dealing with the non-ideal column. So the real column has the initial imperfection, initial crookedness, and how to deal with that, how to estimate the right magnitude, right amount of force to be provided for the bracing, how to get the right number for the stiffness of the brace. That is the crucial points for the structural design of the bracing in steel structure. So I brought you here the papers, which is by Joseph Yura, that we know him very well already, right? So Joseph Yura wrote this one, and it was published in 1996 in Engineering Structures, and you can download this from the website, and I will also provide this piece of paper in the Google Drive for this class. Okay, and Yura is from the University of Texas at Austin, Hook 'em Horn. Okay, so yeah, I used to tell you that he was still teaching at the time that I was studying there, around almost 15 years ago. I don't know where he is now, on Earth or somewhere. But Yura revisit the Winters paper and improve many points in this paper, so we'll be looking at this together. I don't see the screen updated. I am wondering, is there anything wrong with the screen or not? Okay, it is okay. I zoom in, and maybe that's the best that the zoom in can do. Alright, so let's go through this together. Winter classic bracing paper is reviewed, and his method for full bracing. The emphasis is going to be here at the full bracing. We need the bracing that enable the column to develop the full load, and full buckling load means the between two supports is gonna form the half sine curve buckling. It's extended to cases when less than full bracing is used. So this idea, the development of the formulations done in Winter's paper is right when the system failed, right when the column buckle, right? But in Yura's paper, it's gonna track from the various limit states of the structure, so we can see how the system behave, and this enable us to visualize the behavior of the brace much better. Okay, full bracing as redefined in this paper permits the column or beam to support load levels corresponding to an unbraced length of KL, where L is the distance between braces and K is effective equals to 1 using Winter's rigid bar model. An approximate buckling load of the member, blah 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 blah. Alright, fine. It is also shown that Winter's model, rigid bar model, can be extended to cases where the brace spacing is unequal. Well, previously, right, in Winter's paper, he derived several cases of which the brace was installed to the side of the column. But that's for the equal spacing between the brace or between the springs. Yura try something else like this. What? Sometimes the pen is so sensitive. Sometimes it is not sensitive at all. So Yura came to something like this in the derivation here, but we do not need to spend time looking into the detail. I just want to say that he successfully derived the case like this, where the brace is not installed just right at the middle, but we can do all of this using just the numerical techniques. We can use the eigenbuckling codes you have seen. I developed it for you so you can play with that, and you know, it is more flexible to handle many different cases rather than just a few like this. But again, this is in 1996, so this is right now 2020. It is almost 25 years ago, and some of these things is so valuable back at that time, to have the behavior and information like this visualized. So you can go through the introduction. I think I may not need to get into the detail of the introduction paragraph, but we'll look into this. Yura has covered, and he talks about the ideal brace stiffness that was derived. And for the column with one bracing point, the ideal brace stiffness was 2 PE over L. Yeah. If you have 2 points, it turns out to be 3 PE over L, and then so on and so forth. So those are the things that we have the tools to develop, and you can just download the code and play with it, because I just released the code. I just put it on the drive so you can play. The thing is that something like this can be done as well, and here you can just use the code. This axis, this axis, horizontal axis, is actually the brace stiffness, and the vertical axis is the critical load, critical buckling load. So if you keep increasing the brace stiffness until you reach the critical buckling load and plot, as we did, I think you have seen that I put some brace stiffness, I get some force, but I just didn't plot it out formally. And once we come to the ideal stiffness, then we get to the number of the anticipated buckling load. And when we provide more and more and more stiffness to the system, you cannot get anything better than the buckling load. That's because the full buckling has been developed, and you will not get anything more than that. So that's the fact. And so this can be plotted, and when you have the provided stiffness, actually I used to talk in the last week that if I have time or if I have a good mood and too much energy, I might bring you through the plotting. Maybe it could be early tomorrow before the class, before the official class time at like 8:30. I might start at 8:00 to bring you through the code that will be used to show how the deformed shape at the buckling looks like, because the code that we have can produce the eigenvectors. It returns us the eigenvalues, so it is very easy to just use those eigen results and plot it out. But anyhow, this part here, it shows that with the provided brace stiffness less than the ideal stiffness, the column fell in this shape, so it looks like just the one half side curve developed at the failure. But as soon as the provided stiffness is reaching to the beta I or ideal brace stiffness, that provides the full brace. Well, again, this is for the perfect column, alright, perfectly straight column. And this just gives you the idea about the stiffness of the brace and the column capacity, regardless of how much deformation it undergoes, regardless of how much bracing force it has. Alright, I think this has to be highlighted because it looks like we have a lot of information from this graph. But the thing is that we do not have quite a lot of information as well. So you do not know how badly it deforms in order to achieve the ideal load or full load. How much force we need to provide. It might be extremely high in order to achieve the full load. So developments in this paper is going to visualize you that thing, but at least for now, what we had so far from the function in octave, we will be able to produce this relationship. So I hope that you might play with it. It is not difficult at all to go like that. And once you achieve that full brace stiffness, then you get this buckling shape. Okay, you form one whole sine curve buckling instead of half sine curve. All right, and then the L is given by this length. Okay, the length where you need to develop the full brace capacity. You want to develop the buckling over this and over this. Okay, just these two area. Okay, now we come to here. The L is already defined. You know the P, which is the buckling load, critical P. This is just the explanation I just have gone through so far, so we can move to the next page. And to the next page, let's take a look at this picture together. Well, Yura has defined the coefficients in a different way, like changing the spring stiffness to be beta rather than the K. So let's reset what we have in our mind, and let's take a look at this together for once again for the new notations he made. Okay, so I put it down here. So first of all, let's generalize the issue a little bit because we are going to see two different cases. So first of all, this is unloaded before the load. Yeah, don't call it unloaded because unloaded may give the sense that we load it already and then we unload it, so it is unloaded. But the left one here depicts the column that is not perfectly straight. It comes with the initial imperfection delta naught, and in fact the delta naught can be represented by something. I still remember that we have it can be given in terms of the length, and okay, so it can be something like this, the length and divide by 500, okay, whatever number, but it can be defined in terms of the length. Okay, and the column is attached to the spring. This spring is the brace. Okay, so spring stiffness is given by beta. At the initial state, before the loads happen, you do not have the point axial force applied like this, and the spring has no resistance because the delta naught is coming along at the first step, at the first stage, and the brace is attached to the column which is having the initial crookedness, so there is no force in this spring. But when the column is loaded at the top, you apply the axial force P. So from delta naught it turns out to be delta T, and from delta T here you have the deformation, lateral deformation of the column, such that the spring is loaded, and of which the magnitude of the load is going to be I'm gonna write it down. So it is going to be beta multiplied by delta T delta T minus delta naught, and then what, divide, no, not divide by anything. So the bracing force is simply equals to the stiffness of the spring beta multiplied by the deformation of the spring, which is the delta T minus delta naught. So what if the delta naught is equal to 0? Then it's going to be equal to delta T, just that. So first of all, the ideal brace stiffness is revisited first. So this is the top piece of the column, and as you have learned that the concept of the fictitious pinch was adopted in the previous paper by Winter, so it is possible to cast the equilibrium equation of this piece of column, the upper piece of the column, using just the force applied, axial force, and the horizontal force which is coming from the support. You do not have the moment here as it is the fictitious hinge, so it is simply just 0. Well, as you might remember, this is the point where we call it inflection point. So at the inflection point we do not have any bending moment there. Without bending moment there, then internal force is internal moment is 0. So the only two things that contribute to the equilibrium of moment about the point are the P times this distance, the delta T, and the L multiplied by beta delta over 2. When we talk about the ideal case, the delta naught is 0. So this I list out that if the initial imperfection is 0, well, that means the ideal case. And the above equilibrium equation can be casted in the following way. So the P times delta equals to okay. But the beta has to be beta ideal, because the fictitious hinge condition will not occur if the beta is lower. So this is for the ideal case development. You end up with the beta equals to 2p over L, where the P is the load that you require, which is the buckling load of the column, divided by L. Turns out to be the stiffness of the spring of the brace. Now, the derivation will be extended in order to cover the possibility of having the delta naught. So, in reality, I would say so. In reality, the delta naught is not 0. Okay, and as the delta naught is not 0, we will cast the equation in a little bit different way. So instead of P times delta, it is the P times delta T, right? Equals to this part here, the beta times the delta. So the beta times the delta, it will be just the delta, well, or the delta T minus delta naught, okay, and then multiply by L divided by 2. So we will rearrange all these terms. Just expand P times delta T is like that. Beta L delta T over 2 minus beta L delta naught over 2. And put together the delta T in the same place. And we will get the delta naught. If we just multiply through, delta naught is moved to this side, and we have the this minus the P times delta T, and then delta naught is equal to delta T 1 minus P over beta L and multiply by 2. So finally the delta t is given in terms of delta naught and the denominator 2p over beta L. Well, the thing is that it is sort of frustrating around here. I just repeat all of this, but it is quite frustrating around here because Yura just jumps through very quickly from point to point. So ultimately, in the derivation, you just pops up with this expression, and maybe it is quite a jump, and then you are not following. Okay, why are this going on here, whereas you have something over here like this. Okay, so yeah, this is why these things are coming up. And we have the possibilities to rewrite this equation. So first of all, for the possibilities that you have the beta I, you have the ideal brace stiffness for this case. So if the brace stiffness is ideal, then you have the 2 times the PE, which is the buckling load, over L. And as you have this number, PE turns out to be beta L over 2. Right? And now it is possible to plug in. So first of all, this can be plugged in, and then you end up with delta naught divided by 1 minus 2 times P, and then you substitute the beta I over beta IL. Copy and paste it. And instead of beta I, just substitute that whole thing. So beta I is equal to this. Okay, cancel out. Turns out you get delta naught over 1 minus P over PE. And if you do it in another way around, so instead of plugging in the beta, we are going to plug in the P. So we put the Apple Pencil. Someday it is not sensitive at all. I like tap tap, double tap, double tap. It doesn't change. Today it is like what, coming back to work or something, and I don't want to change from pencil to the eraser, and then it just keeps changing with a very sensitive touch, and then it changes. Yeah, something frustrates me in the very in the early morning time. So 2 times PE over beta L. Okay, we substitute the terms PE into this expression here. And then you get the delta naught divided by 1 minus 2 over beta L. And you have the PE, right? And then let's see, what is the PE? PE is given by beta IL over 2. So beta IL over 2. And it is clear that we can cancel this and cancel this. So ultimately we end up with the delta naught over 1 minus beta I over beta. That's it. Well, it looks easy, it looks stupid, but believe me, it will take you quite a while to just come from this point here to this point here. You're gonna have a lot of fun if you don't watch this video and you try to struggle from this point to that point, because this is all in the Yura's imagination, which is not explained in detail in the paper. Okay, so what is the use of this information, of this sets of equation? Well, this one is the part that enable us to understand the behavior of or the response of the column that includes the initial imperfection. So we'll see. You can come to this graph here. Over here, the plots between first the P over PE ratio and the delta T over delta naught. If we can rearrange, right? So the delta T over delta naught, you just simply move the delta naught to the other side and then plot versus the equals to 1 divided by 1 minus P over PE. Just like this. So this equation can be plotted, and that turns out to be the figure you saw in that page. This figure is very useful because you can test it against different numbers of delta naught. Okay, but that is not the big deal. The fun part is to be able to see that when the P over PE ratio is achieved, and it will not be greater than 1.0, right? So you can plug that in. I can just copy this one and put it just on the side of the figure. Copy. Yes, it is here. Okay. The observation is that the mobilization of the load, if you compare wait, you need to vary the beta value as well. Okay, we still need to do some other things. Sorry. Yeah. So from this point here, see. We need to put the beta value. So the beta you can put the beta equals to beta ideal in there, and if it is the beta ideal, then okay, the ratio of POPE, the scaling of the POPE is gonna be changed, right? So let's just look at it this way. So this one is the curve associated with the beta ideal. Let me copy the page. Copy, and I'm gonna paste the copy page. Done. Alright. The same. Erase all. Delete. Okay, get it back. I'll take this line then. And yeah, look at this in the next page. So here's the point. We are looking at this expression, which is made for exclusively for beta equals to beta I. Exactly, you get this one. So what if the beta is not just beta I? Because in the graph you have the B2 beta I, 3 beta I, and so on and so forth. So how do you come up with those graphs? It's possible. So if you plug in beta equals to 2 beta I, it's gonna be over there, right? Yeah, just like that. And then the 2 will be there and will be there. So for other cases where the for beta is equals to let me check if I use something. Okay, omega times beta. Okay, omega times beta I. So omega is the number of times, like 1 times, 2 times, 3 times of the ideal brace stiffness. Then you're gonna have the signature omega in the expression you see above. So let's make a room for omega. 1 over omega like this, then leave it there. Beautiful. And then let's get these curves by switching to the other platform. So switch to here. Back to Microsoft Excel. Okay, make it bigger. So delta t subscript t divided by delta naught is 1 column. And another one, the POPE is the y column, y axis. So the extent, it starts from the value is equal to the delta t over delta naught. We got to look back into this. So the implication of delta t over delta naught, total delta divided by delta naught. If you have the original delta naught being some number, the delta t cannot be less than delta naught, right? If you come to the scene here, and so at the initial condition like this, your delta t is equal to delta naught. That's what I am trying to say. So you do not have the minimum, the smallest value of delta t over delta naught is equal to 1.0. That's the point. And if that is equal to 1.0, over here I'm gonna put just 1.0. And I can include the omega parameter just alongside here, and that was supposed to be omega if it is equals to 1. That is the ideal brace stiffness. So this turns out to be if what is the expression? If the 1 divided by 1 divided by 1 minus sorry. We got to start, in the other way around. So POPE has to start from 0. Okay, then delta will be computed from the POPE, okay, according to the equations that we cast like this. The POPE come first, and then you compute this from the function of POPE. So okay, I switch it around. So POPE has to start from 0 when you do not have any axial force, and then make it 0.1, 0.2, and so on, all the way to 1.0, and that is the cap. Or should we just do it the other way around? I think it is sort of counterintuitive here. If we switch it the other way around, to write POPE with in terms of the delta, what do we have? 1 it's going to be delta naught over delta t equals to 1 minus 1 over omega p over PE, like this. Just move it up, take that down, and then you want the POPE only. So what would that be? The P over PE is going to be 1 minus delta naught over delta t, and then scale by the omega. Oh. Right. So I take the POP to the other side, 1 minus delta naught over delta t, and then the omega goes up. Right. This is the expression for POP, and this has to be less than 1.0. Just that. So I will switch it back to Microsoft Excel. It is possible to do it this way, but the thing is that when you reach to 1.0, you cannot go further. So the formula has to be from here, and it will be increasing to, I gonna make like 1.1, 1.2, like this. Then 4, 5 to 20. Now this expression is going to be if the POPE is coming from the omega, which has to be pinned. So I pinned the cell like this, multiply by 1 minus delta naught over delta t, but over here is a delta t over delta naught, so 1 divided by this. Okay, and if this is smaller than 1.0, then it is this number. If not, it is 1. So this is 0, and then we copy it down to 20. So this is the first curve, which is coming from the beta equals to the ideal breast stiffness. I will just paste it just alongside, and I'll paste just the number. Okay, like this. This is for beta equals to beta ideal. Okay, that means the omega is 1.0. Now let's take a plot and see how the curve looks like. There it is. 1.0, and I'm gonna format the axis and keep everything at just 20. For this one, I'm gonna specify 1.0. Okay, like this. Chart title, I take it off. We do not want to see anything from that. What is the implication we can read from this figure? We know that when you start the delta t over delta naught come from 1.0, we have the initial out of straightness, and then this case we have the spring stiffness, which is equals to the ideal stiffness. We start from delta t over delta naught equals to 1, and it takes 20 times of the delta naught, okay, 20 times of the delta naught in order to mobilize the strength, which is as much as 95% of the expected strength. 95%, we can just look a little further. Okay, yeah, this is just a perfect 95%. So if you want to achieve to something close to 100, let's see, 50, if we put the 50 times of the delta naught in order to get the 98% of the buckling load. You use 90% of the delta naught. Well, I will switch back to this screen. $98% of PE. You need 50 times of delta naught, and generally delta naught is controlled to be L over 500. L over 500. So if you need 50 times of L over 500, that is equals to 10% of L. 10% of L. Is that large? Your column is, let's say, 3 meters. In order to mobilize to 98% of the expected strength, you need to let the brace move to 10% of the length of a column, which is 30 centimeters. That is going to be ugly. Alright? That is going to be really, really ugly to have the system deform by as much as 10%. And I'll switch back. So this one here is ineffective. The plot here visualizes us quite a lot. We get a lot of information, and we understand now why this ideal brace stiffness proposed initially is not good for the design, because it just takes too much deformation in order to mobilize the strength. So let's take a look at the brace stiffness, which is a little stronger. So we make it 2 times as much. When it turns out to be 2 times as much, this is all we get. I will copy this and just put this alongside. I get the values and numbers, okay, formatting, and the beta here is equals to 2 times beta ideal. I come down here, I select the data, I add the data, then X series is the delta value, and the Y axis is this one, and there it is. Now you can see that you just increase the brace stiffness for a bit, which is about 2 times of the ideal brace stiffness, and you end up with the full mobilization of the axial force. So the deformations which is around here actually is what? Just 2 times, just twice of the delta naught, and then you get the 1.0 P over PE ratio. This is a very good deal. You just move to this much. It's just 2 times of the initial out of straightness. So if the initial out of straightness is L over 500, you will need 2L over 500 to mobilize the 1.0 or to mobilize the buckling. So let's vary this a little bit up and down, and then we will wrap up about this curve. I put the 1.5 in. And then I'm gonna put the 3 in. Okay, 1.5 and 3. So add these two in and we finish up. 1.5 is this one. Okay, and add one more in, the 3. So the 3 okay, just it. Behavior just looks improved, right? It improved. Wait a minute, I need to draw into this direction. So the least brace stiffness you provide, it gives you quite a very soft system, and it takes you like forever. It takes you like infinitely large deflection, large lateral deformation in order to reach to the 1.0 P over PE ratio. That is bad, and you do not need this in your design. Alright, because you are going to need quite a very large bracing force. Capacity of the brace will be really large. It's not a good idea to do that, and your structure will badly deform. That means it is not usable. But when you just increase the stiffness a little bit from just 1.0 times the B ideal to 1.5, you get the gray line. For the gray line, you mobilize the full strength at somewhere around 3 times. 3 times of the initial delta, initial out of straightness. It looks better. When you increase the beta to 2 times of the ideal brace stiffness, you need just 2 times in the orange line. So 2 times of the ideal brace stiffness is this number, this line, 2 coming down to 2. And if you keep increasing the beta to 3 times of the ideal brace stiffness, you need just 1.5 times. So it improves a little bit. Then you can keep adding more and more, but the behavior will not be better than just having like pretty much like a straight line going vertically like this and go flat. So if I say like to erase this one, I make this I'm gonna put like 1.01. Okay. I'll make it a very large number, right? This the best that you will get. What is it? Oh, it is linked like that. Okay, fine. So this is the best that you can get in the yellow line. The graph just go like a straight line from this point and there, which is very expensive. To move from the point somewhere around here to here, it is infinite. So you will need the number of the ideal brace stiffness to be somewhere around just 2 times or 3 times, and that will be enough for the purpose of bracing the system in order to be able to go all the way to the full buckling load. Okay, I can just give you this Excel sheet anyway. It is easy to make. It is fun to make though. Alright, so this is the one plot. Well, let's take a look at another thing. Come back to here. So if I think all of these are the explanation of what we just have seen so far. So they talk about the load. When the applied load is within 5% of the buckling load, that means that 95% of the buckling load it is as close as 5%, but you're gonna need 20 times of the delta naught, which is ridiculous. If the brace stiffness twice the value of the ideal stiffness, the equation 3 gives much smaller deflection. Equation 3, which is this one here. But again, if you just read this paper alone, you might struggle. How does it give that number? Yeah, so it just jumps around a lot. As shown in figure 4a, when the load just reached the buckling load, come on. When the load just reached the buckling load, delta t equals to 2 delta, okay, this is 1.5, okay, we solve this. The larger the brace stiffness, the smaller delta t. For figure 3 and equation 2 and 3, the force in the brace is given as follows. Figure 3, where is it? Figure 3 is this one, and equation 2 and 3. Equation 2 is this one here, and equation 3 is this one here, and then he pops up with this one. So force in the brace is equals to B times the delta. B times the delta is it is nothing, right? Beta times delta. Beta is the brace stiffness. Delta is the delta T minus delta naught. Is it too much coffee for today? Okay, right? So what is it? Delta naught plus delta 2 times P. It is substituted from here, right? Beta equals to 2 times P. Okay, so you come to this point. They don't put it in the delta T form. And then things inside, delta naught plus delta is actually the delta T. Just a different way of writing things out. So the delta T is given by this and given by this. That's the point. So in order to be able to plot this one, this is the P over PE plot versus the bracing force, which is given in the percentage of the P. Okay, then let's take a look at the equation we had there. You better plug in this one rather than looking at this, because if you look at this point, you will not see the possibility how you come up with the different beta value. You want different brace value, but in this expression the beta is not a part, so you'll be frustrated and you will not be okay with this given equation. If you equate this side to this one, you cancel all this out, then you can plot just P and the beta value. You do not have the bracing force, right? I guess I can point out the pain that you will have if you just read through the paper. You will not find the place. If Well, if you read and you are sleepy at that moment, you may not have a question. That's my point. But if you read and you are so concentrated, you will find that this is so annoying to you because the bracing force cannot be related to P over PE by incorporating the beta value in there. So okay, let me just put this in the next page. So FBR the bracing force FBR is equal to the beta multiplied by the delta. And it turns out to be is from here. The beta is given by this one. So 2p over L and then 1 plus delta naught over delta. Am I right? 1 plus delta naught over delta. Okay. And the whole thing is multiplied by delta. So, okay, this is expanded out a little bit. 2p over L, and this is just the delta plus delta naught, which is equals to 2p over L times delta T. And delta T is given from above. That makes delta T equals to 2p over L, and delta naught is there, and 1 minus p over omega PE was in place now. Okay, 1 minus 1 omega and p over PE 2p. Okay, that is. So the omega is there. And we have the 2p over L. Let's see. 2p over L. F is given in terms of percentage of the P. So I rewrite everything in here. Finally, the FBR is divided by P, and we're gonna need the percentage of this one, equals to delta naught over L delta naught over L of 2 divided by 1 minus P over PE. Turns out to be this form. Let's see if this is a form that makes a graph. The delta naught has to be fixed, right? And the output P over PE and FB are percent of the P. Okay, so this has to be given. So you can see that in that it said that the plot is specifically for this case, so it is given. You can change it if you want, and this is also given. And this is the plot number what? This is figure 4b. And this is figure 4a. This will be changed to percentage, so it's gonna be multiplied to 100%. Okay. Let's switch to Microsoft Excel sheet. One second. Okay. So we have the come back first. The plot is going to be having the vertical axis P over PE, horizontal axis bracing force. So this is going to be the vertical axis. We got to move things around again in order to express the P over PE in terms of the other things. So if I make it this way, let me on this side 1 divided by this ratio, and then the FBR over P is in place there. So we have 2 divided by the thing, then switch it around. So we have the 2 and then divide by this thing here, and then you get the 1 minus the which is like this, and switch around So I don't want to write too much. Got it here. P over PE to the right, and then move this to the left. Yeah, it will work this way, right? Minus P over PE turns, okay. And the whole thing is gonna be amplified by the omega. So you scale by the omega. That's it. We are going to compute this expression. Come back to here. I need this. So I can use it. This is not delta. This is the FBR, bracing force divided by the P, which is the percent. And we are going to cover to somewhere around 3-4%. The expression here, bracing force, second, I'm figuring out if the POPE is 0, the bracing force has to be the ratio of the bracing force. We are talking about the ratio. So P over PE, if it is 0, this part is gone. You have 2 multiplied by the initial out of stiffness ratio, the delta over L, delta naught over L, which is like 1 over 500 or 0.002. Okay, 0.002. None of this, so it's gone. You have 2. You have 2, and this is somewhere around L over 500. So you get the L over 500 multiplied by 2 divided by L. L cancel out, so you get 2 over 5. 2 over 500. 2 over 500 is 0.004, right? 2 over 1. 1 over 500 is 0.002. Yeah, so 2 over 500 is 0.004. 0.004 is equal to 0.4%. So that is going to be the starting point. And 0.04%. No matter what omega value is, if this is 0, then it doesn't really matter. So the whole thing is 0. So no matter how much the omega is, if the given delta naught over L is according to ASTM, which is L over 500, then you end up with 0.4%. So 0.4%. None of these are going to be used though. 0.41. We're gonna do it all the way to 1. The curvy one, okay, make it all the way to 4 then. Okay, too much. I think the sensitive area is sort of like 1. Okay, just make it to 1. And then 1.05. So it's gonna be easy to 2 to 3 to 4. And now the expression will be given by I put a 1 first, and this is going to be if omega multiplied by 1 minus this was supposed to be 2 well, divide by F bracing over P, which is this one, but I've got to multiply by 0.01 to turn it back into the fraction rather than the percentage, and multiply by 1 over delta naught over L. 1 over let's make it here delta naught over L, and the another one, and I will lock this and this. So if this is good, if this is less than 1, then we're gonna put this in. Just I make it 0.01, 0.001. This is the delta naught over L. So this is 1 in 1,000. If we put 0.002, yeah, this is gonna change. Do we have anything we need to incorporate? Some other things. The formulation we had. Okay. At 0.001, what is that? Why is it 0.5? Oh, for 0.001, the calculated value here is okay. Calculated value here is different. So the 0 will start from the different FBR over P, right? Okay, so this is corresponding to 0.002. Okay, this is calculated from using this delta over L equals to 0.002. Okay, What else? We copy this all the way and we get this. So shift, copy and paste somewhere there, and this. So this is for omega equals to 1. Let's try omega equals to 2. It doesn't change this, as I mentioned, of course. So for omega equals to 2, this one, we don't need the formula. And later on, equals to 3. And that's it. So I just need this beta equals to beta ideal. This is for the first case. Beta equals to 2 times. This is the second case. And beta equals to 3 times. And the third case is just there. So let's plot it out. And insert. Oops. And am I sorry. Oh, sorry. I didn't change the screen. Sorry. Okay. So you okay. I didn't change the screen back here. So formula is already casted this way, and that is consistent with the development in the iPad. So I changed the omega from 1 to 2 to 3, and then I put all of the results back in this area here. Okay, so I'm now going to plot all of this out. Insert, and we need the graph. Okay, and put it all the way back up. Okay, it's there. Delete the chart title, it takes a space. And we add more. Select data, we add for the and we add another line which is from the 3 times the ideal brace stiffness. And there it is. Okay. So now we can see the issue is quite clear to us in the point of view of the bracing force. The horizontal axis depicts the bracing force. This starting point here is going to change if the initial out of straightness ratio delta naught over L is changed from 0.002, or this is in fact this is 1 over 500 of L. Generally, this is the number given by ASTM, so it is fixed to be this one, right? So if you change from 0.002, it's gonna be moving. This point is gonna be moving, but the omega value will not be changing or moving this value here. Okay, it is affected by this delta. You can look at the structure of the equation, and you will see why it doesn't affect. Alright, so I changed the omega values or the stiffness. This is the smallest brace stiffness, which is equal to the ideal brace stiffness. I increase it up, I come to here. I increase it up to 3 times of the ideal brace stiffness, I come to this far. So the meaning is that the less the brace stiffness, the higher bracing force is going to be. So I come back here, I draw you maybe one line like this. If I want to come up with this force magnitude, which is somewhere around, if it is just 80% of the PE, you find that the bracing force is somewhere around 0.5 or 0.6% if the brace stiffness is high. If the brace stiffness is just 2 times the ideal brace stiffness, it increased from this to this, so it might be around 0.7. And if you only provide the brace stiffness equals to the ideal brace stiffness, then you need 2%. Okay, you get the meaning of this graph from this interpretation. And if you move further, like to 90%, at 90%, this is terrible. You need 4% of the P. So if your column is resisting 100 tons, this is 4 tons already. Whereas this is just a fraction. It is less than a percent, so it is less than 1 ton. And also this one is even smaller. So the higher brace stiffness you provide, the less bracing force you will need. The thing is that when you put the large cross section, you have 2 things in the same time. So you will have the large stiffness and the large stiffness and the large force carrying capacity, right? So there will be some optimal number somewhere around 2, 3. That is just good, because if you provide more and more and more stiffness, then the bracing force will be less and less and less, but your capacity is proportional to the stiffness, right? So you have more than enough capacity, but the bracing force is very small. That's the thing. So you will just find the point that it is a good and optimal point for the design, and the design code will recommend you some number, and we are going to talk about the design code point of view later. If it might be tomorrow. Okay, and what else that we have in this paper? So I switch you back here. Now I should have cleaned this up before. Delete. Okay. Right. So you can read through, but I think it will take more time to go through and to be able to convince yourself at so many points. What is this here? Last year I derived it in a different way. Seems to be easier for this year. Expression. Okay, fine. These 2 pages are the same. Actually, I should delete this one. This is from the last year and we are not using it. So we just use this one here. This is used in our plot journal. Okay, we plot. I erase this one. Trash it. It's just different, but well, same thing happened. Okay, so this is not in the previous page anymore. And what else? Okay, I don't need this. For this one here, I should erase this because this is good for just one equation. But I might say something like Okay, yeah, it should be this equation. Copy and paste there. So and I say something like here is the beta L. Okay, so I write something beta L is equals to omega beta I, and I specify clearly here that the beta L is this thing, so the omega is substitute, and then we'll be able to get all the graph like that. Okay, so this graph is clear, this graph is also clear. We are very good with this paper, we understand it quite fully. What else? Actually, I intend to play with this graph by using the geometric stiffness matrix approach and introducing the initial out of straightness like this, and we'll see how the delta T over delta works. Okay, I never tried this before. I should. So let's play with that together. And the rest of the things that Yura come across the other thing like this, and actually it is quite interesting for us to play with the code in Octave that we already come up with, and it actually can produce this thing. So this is the column that is supported by 3 bracing points, and this bracing stiffness beta is changing, so it is increasing when the beta is equals to 0. Okay, so that means you do not have any stiffness for the brace. You have 1, 2, 3, 4, right? So your buckling load is just here. Here is 1 over 16, right? Pi square EI over L square. So 1 over 16 is some... Oops! Come on! What is this? Oh, it's all gone. Why is it so easy to just switch to that setting? So 1 over 16. Let me get the calculator and hit it. 1 divided by 16 by 0.025. And then you increase to some point, and the buckling is changed from half sine curve to 1 full sine curve like this at this value, and then you have this buckling shape until your stiffness approaches to this new number, and then you can form this until the stiffness is big enough. Then you can form 2 sine curves. So this is interesting, but it is going to be laborious for the hand derivations. It is possible. It might be fun for you, but I think we might be able to do something fun using the buckling code that we prepared already. Okay, so we run out of time for today. I'm gonna see you again tomorrow, and we're gonna pick up from this point. Thank you. See you.